So let's go back to the frequency response. So the Z transform of this moving average low pass filter is given here. So when we replace Z by e to the power of j omega, we will have this thing here. And usually we're interested in a magnitude and phase of the frequency response. So we can take the magnitude operation here and the phase. So we can compute using Python. So here I'm importing SymPy, defining Z as a symbol. So we'll have Z transform as a polynomial. So this is what we're doing here. So we flip the coefficients of the impulse response, and then we construct a polynomial with Z to the power of -1. So here what we have is the Z transform. With a bit of expression manipulation, we can change. So here it's easier to see that we have a pole when Z is equal to 0 and a 0 when Z is equal to -1, and we have also this gain factor of 0.5. And now if we replace Z by e to the power of j omega and we choose a desired frequency, so we're choosing 100 points between 0 and pi, so pi will be until half of the upper circle on the complex domain. So we're initializing a frequency response with complex zeros, and here we are replacing Z by e to the power of j omega. And then we can compute here, we have the magnitude response for 100 points. So we see that it's a low pass filter here. This is a normalized frequency, so pi is 3.14 here is the Nyquist frequency. And we see it's far from being a perfect ideal low pass filter. If we plot in the dB scale and also the phase, we will have here is what we're doing. We're plotting now in the dB scale, and we're also plotting the phase. So we see it's a linear phase with a slope of 0.5. So here we see the normalized frequency, so pi is the Nyquist frequency, and we see the slope of 0.5, so it's a linear phase. And here we can see the magnitude in the dB scale